In this video, we are going to talk about equilibrium and vector triangles. In the previous video, it ended up by when I was talking about the fact that when you draw the vector triangle, it must be a closed triangle when the forces are in equilibrium. So it must form a closed triangle with T, W, and H as shown there. So the forces must act in the same plane. That must be coplanar. The forces form a closed triangle, and the forces must all act through the same point. They must be concurrent. Now we're going to start off this video by looking at an example of this. We've got three forces that are shown that are in equilibrium, and using the triangle forces, find P and Q. So when drawing the triangle forces, make sure you draw them head to tail. Head to tail. Right, so we're going to try and do that. We've got the 20 Newton force going down. That's 20 newtons. And then we've got P going up. P is at 60 degrees to the horizontal. And then we've got Q, which closes the triangle, moving upwards. And the angle here should be 40. So if this angle here is 40, which means this angle here will be 40. And then this one will be 50. You have got to draw these vectors to scale. Remember, you draw these vectors to scale, and you always draw them head to tail and find out what you are going to get. Using the resolving method, this is how, this hasn't been asked, but I just want to show you how you can use the resolving of vectors method to find that. So this is 60 degrees, this is P, this is Q, and then this is 20 newtons. Now, if you resolve these to the horizontally, you have got P cos 60 degrees is equal to Q cos 40. And then vertically, you're going to have P sine 60 degrees plus Q sine 40 should equal 20 newtons. Here, the first case, you could just make P the subject. So P there will be equal to Q cos 40 divided by cos 60. And then substitute it into here. So wherever you have that, you just write Q cos 40 over cos, this is cos 60. So cos 60 times sine 60 plus Q sine 40 should equal 20 newtons. Now if you do the maths, let's see, cos 60, so this is 1.32 Q plus 0.64 Q is equal to 20. So this is plus 1.32. Right, to get Q is 10.2, and then you go back and substitute it into that one, the first one, to find your P. So it's going to be P cos 60 is equal to 10.2 cos 40 degrees. So P will be equal to 10.2 cos 40 over cos 60. And you should get 15.6 newtons. All right. Conditions for equilibrium. For a body to be in equilibrium, the turning effects of the forces must balance out, as well as giving a resultant force of 0. So the two conditions are the resultant force in any direction must be 0, i.e. there mustn't be any translational motion. And then the second condition, there mustn't be any resultant torque about any point. So resultant torque about any point is 0. There is no rotational motion. Now we're going to talk about parallel forces. If you suspend a 3 Newton weight from a meter rule as shown, and set x1 to be 0.2, x2 to be 0.6 meters, then you're asked to find the direction forces R1 and R2. You can apply the conditions for equilibrium to solve this. So upward forces, direction forces going up, must equal the weight going down. So we're going to say R1 plus R2 is equal to 3 newtons. That is the total weights here. or the weight of the weights here. And then that's the first condition for equilibrium. Then in the second condition for equilibrium, we can take moments about any point, and then we get 0. So suppose we take the moments about R1. So R1 becomes our pivot right at that point there. So we have our clockwise moment is W. Wx1 is our clockwise moment. And then x1 plus x2 times R2 is our anti-clockwise moment about this pivot here. Then when you do that, you're going to find that 4R2 is equal to 3 newtons. And then you find R2. You get it as 0.75 newtons. And then R1 will be 2.25 newtons. Just do it and then comment. Tell me whether you're finding any difficulties. You could use this again as your pivot that is at R2, which means you're nullifying the effect of R2 in the equation. So wherever you take your moments, which means the effect of that force is nullified at that particular time. So here, if you take moments about this one becomes W times x2. That would be an anti-clockwise moment. Then R1 times the total distance x1 plus x2 will be your clockwise moment in that case. The second example is that of a van and a trailer across a bridge. So it says the axle loads and the position of the vehicles are shown. The single span bridge is supported at points 21 meters apart. So that we've got 7 plus 3.5 plus that, that's 21 meters. Calculate the vertical forces at each of the supports caused by the van and trailer on the bridge. So, and then it says find the support forces, which will be just the reaction forces right there. So what you do, you can take moments about the LHS, which is the left hand side here. So which means you've got how many clockwise moments? 1, 2, 3. So this one will be 4 kilonewtons times 7 plus 10 kilonewtons times the total distance, which is 7 plus 3.5, and then plus 8 times the total distance, 5.25 plus this. So all these will be your clockwise moments. Then the anti-clockwise moment would be this reaction force right here times the total distance, 21 meters. I think that's what you're seeing here, vertical force times 21 meters. So you get the vertical force then is 12.3 kilonewtons. Now to find this other vertical force, you use the second condition for equilibrium, where you are saying these forces going down should equal the force going up, which is from the supports. So 4 plus 10 plus 8 should equal the 12.3 that you found plus this x. Then you make x the subject. You find your force to be 9.7 kilonewtons. Then I'm going to end this video by talking about non-parallel forces. An example on non-parallel forces. A sign of weight 50 newtons is hung from the end of a uniform bar of length L and weight 20 newtons. The bar is hinged to a wall and held horizontal by a wire attached to the wall at 30 degrees to the horizontal. Find the tension in the wire. So what you could do there, your two conditions for equilibrium must apply. That is, the sum of the forces going down should equal the sum of the force going up. Right? So the force at the hinge plus this T, the component of the tension upwards, should equal these forces downwards. So I think there you are. Here you've got the reaction at the hinge there. If you resolve it so that it's perpendicular to the uniform bar, and then also resolve the tension so that it's perpendicular to the uniform bar, add the two forces, they should equal the sum of the forces going down. Now what do you do first? You take moments about the hinge so that you nullify the effect of the force that's coming from the hinge. So if you take moments about there, then you only remain with this force here. So it's going to be 20 times the distance here, 20 times half L, because this is the weight which is acting at the center. So since the uniform bar, the weight acts at the center. So half L times 20 plus 20 times L should equal T sine 30 times L. That is our anti-clockwise moment. So that's what you are seeing right here. Okay, so you get your T as 120 newtons. Now then you apply your second condition for equilibrium, which will be R sine theta plus the T sine 30 should equal 20 plus 50. In the horizontal, the forces going to the left should equal forces going to the right. So R cos theta should equal T cos 30, going that way. So you use the two simultaneous equations to find theta and R. So if you do that, you find that the sine theta and the cos theta will give you a tan theta, which is tan theta will be equal to 0.0962. So theta will be 5.5 degrees. Then you substitute into the first equation here, and then you find your R to be 104 newtons. So the tension in the Y is 120, and the reaction at the hinge is 104. An example of a non-parallel force comes from the ladder. So if you have a ladder that is leaning against a wall, you can find the forces that are coming from the wall as well. So let's end this video by looking at this very last one here. A uniform ladder 5 meters long of a weight 200 newtons rests with its upper end against a smooth wall and its lower end at 3 meters from the wall on rough ground. Calculate the frictional force F between the ladder and the ground. And then B, the normal reaction S at the ground and at the wall. And then C, the magnitude and direction of the force X exerted at the bottom end of the ladder. Now, one thing to note here, the ladder is exerting a force. The force that the ladder exerting on the ground is going to the right. So since we said frictional force is a force that opposes motion, the frictional force will be going inwards. Now we are told that the wall is smooth. So if the wall is smooth, then there is no friction that is taking place there. If there is friction acting there, then we will have again another force going going down, which is going to be our friction. So which means that the reaction force from the wall and the friction going down will form a resultant force which will be going in probably in that direction there, up at an angle. But in this case, we are lucky because there's no force on the wall due to friction. The only force that's coming from the wall is the reaction force from the wall, because there's an action, so there must be a reaction from the wall. There is no resultant force acting on this system, so which means the S going up should equal the weight going down. That is this first condition for equilibrium. S is equal to W, so S is 200 newtons as well. Then if we take moments about the top of the ladder here, we are going to exclude this R here because there's no distance moved about that. So which means we can say clockwise moments is equal to anti-clockwise moments. So we're going to get our clockwise moments. About there will be the weight of the ladder, and then we do have also the frictional force from there. That is also a clockwise moment going there. And then S has an anti-clockwise moment about there as well. So F times 4, we are saying this, F times perpendicular distance is 4. Okay, so F times 4 plus W is this one, 200 newtons, and it's that perpendicular distance is only 3 meters. This should equal S times the 3 meters going up. So perpendicular distance is 3, because remember our distance is to that part here. So which means that will be this line here is showing us where we should end adding our distances. So if you do that, you find that your F comes to be 75 newtons. And then you get R coming from the wall now. The R coming from the wall also comes to be 75 newtons. Again, what was supposed to help us here is that since there is no other force acting, this force going to the left should equal the force going to the right. So again, this should have given us that this frictional force is equal to R going that way, according to the first condition for equilibrium. To find the angle of R, you could draw a triangle. Then we've got 200 Newton, that's the weight, and then we've got R, which is 75 degrees, and then we want to find this angle here with the horizontal. So we use tan. You can use Pythagoras. X squared is equal to 200 squared plus that. You find x, which is direction force that is coming from the ground. That's this one shown in green. Since we've got F and S, we can find direction force coming from the ground. And then we can also find the angle. Okay, so the angle will be using tan, opposite of adjacent, 69.4 degrees. So that will be the angle that is between direction force from the ground and the horizontal. I think that marks the end of this topic on forces, density, and pressure. You could try and work out the problems that I've worked out. If you do not understand any part, please feel free to comment so that you get help. Signing out.